Good morning and good afternoon, everybody, for joining us today. My name is Roger Frechette. I'm a managing principal with Interface Engineering, and I would like to welcome all of you for joining us for our next installment of our biweekly educational series that we have been offering throughout the spring and will continue to offer throughout the summer this year. This is our second year of providing these educational sessions to our friends and to our clients. And if for those of you joining us for the first time today, just a little bit about Interface Engineering. We are a mechanical electrical engineering design firm. We were established back in 1969. We have 220 plus lead projects that we've completed. We've designed and certified several net zero energy projects and have another 50 net zero energy projects that are in the process of being constructed and certified. We provide MVP, fire life safety, energy, building technologies, lighting design, and commissioning services out of our 7 offices across the United States. So with that, and without further ado, I'd like to introduce today's speaker, Mr. Steve Gross. Steve is an associate principal with Interface Engineering. He is also a lead energy analyst for our firm. Steve is a licensed professional engineer. He obtained his bachelor's degree in mechanical engineering from the University of Tulsa. He received his master's degree in mechanical engineering from Portland State University. And he is a member of the American Society of Heating, Refrigeration, and Air Conditioning Engineers. So with that, Steve, thank you so much for leading the discussion today, and I'll turn it over to you.
All righty, thank you, Roger, and welcome everybody to our webinar today. First thing to mention is I'm the team leader for our building science program out of the San Francisco office. So anything related to building simulation, building performance, sustainability, that's what my team is involved in. So today we're going to talk about facade performance and simulation-informed facade design and how that impacts overall building energy consumption. So it's going to be a whirlwind of information today. So buckle up. And be sure to put your questions into the questions box as they come up, and we'll get to them at the end if we've got time. So just some housekeeping. This is an AIA registered class, so please make sure we've got your information if you would like to get credit for this as continuing education credit. And I'm not going to read the full course description, but like I was saying, this presentation is about facade design approach and how we analyze the facade performance. So the learning objectives I hope you'll walk away with at the end of this presentation is really to learn about the various analyses that we perform on when we're optimizing the facade. And we'll talk about different climate zones and why you might use a different facade treatment or strategy for the facade in different climates. We'll talk again about window to wall ratio at different climate zones and how that may change and be optimized for different climate zones. And then finally, a key takeaway about the importance of passive solar heating in heating dominated climates. And so we'll just jump right in. The overview of this presentation, I'm going to start with just some high level examples of analyses types that you can do with facade performance in mind. And we'll talk about a case study at a high-tech headquarters here in the Bay Area. And then again, switching gears, learning about parametric analyses, specifically with energy and daylighting. And then another case study in a cold climate where we optimize fenestration in Lake Tahoe. Very cold climate, but very sunny. So just to start out and kind of advocate for energy modeling in general, this is the 2030, the AIA 2030 challenge. I hope most of you are familiar with, is really about improving the energy performance of our buildings as we're building them. So the goal is to reduce energy consumption by 70% over a 2003 baseline building, essentially. So at the end of every year, the AIA releases a report card kind of summarizing the performance of all the projects. And what's really stark is an important takeaway here is that only projects that are doing energy analysis and actually modeling their performance are achieving the goal. And so very few projects in general were meeting that the architecture 2030 challenge, because it is a challenge. It's a difficult metric to meet. But what you can see on this slide, the average project doesn't meet the 2030 challenge, and only a few of them actually do. And so what you can see in this graph here is that none of the projects that are not pursuing energy modeling are meeting that challenge. So basically, this won't happen by accident, and you have to make a conscious decision to do this and to analyze the project and come up with the strategies that will get you there in a cost-effective manner. So that's just a little bit of me advocating for doing energy modeling in the first place. So here's just a slide showing the different kinds of tools that we use and that are available out there in the market for doing energy analysis. And the point to make here is it's not just one program, it's a whole suite of software that we're using. Depending on what analysis we're doing, we'll choose the correct tool. And so the top two up here, IESVE, the virtual environment, and Energy Plus are two big, or I call our bread and butter software that we're using for annual energy simulation. And then these other tools are for more specific or specialized sort of investigations, like DIVA and Radiance doing daylighting investigations, Autodesk CFD for doing airflow in and around buildings, that's computational fluid dynamics. Python we're using to develop our own tools to write scripts to manipulate models and process data, things like that. And Saphira, I mentioned this up here is because it's a tool that's it's useful for those doing high level early stage analyses, and often architects and owners are getting into this software, and so we use that as well to try to help our clients out when they're pursuing these types of things. So okay, so just to start out with some relatively easy software that may be actually useful to some of the architects on the call, LBNL window and Therm analyses. So this is a tool that basically allows you to simulate the performance of different glass types depending on the different lights that are composing the total IG or the total glazing unit. So I mentioned this just because oftentimes we are, as a consultant, as an energy consultant, we're helping the architect identify the window and thermal performance of their selections. And this tool can help you save some time to study the thermal performance of your options. If you're working with the glazing rep to select different aesthetic properties of the glazing, you can actually use this tool very readily that will tell you the solar heat gain coefficient and the overall U value and the visual light transmittance based on sort of a custom configuration of the glazing. So it's a really useful tool for providing feedback sort of two directions between my team and the architecture team. And what this also helps you to do, the Therm analysis actually allows you to study thermal bridging between the components of the construction components, the glazing mullions, and the way things are put together. So this is just a view of looking at, on the bottom right here, is looking at how the mullion is actually interfacing, or thermally interfacing with the building structural system. And we're studying the ways to limit those thermal bridging effects. Oh, excuse me. Here's an example of parametric daylighting simulation. So, and this is an example here of just a long rectangular building where it's discretized. So that means we chop up the floor plate into tiny grids, and we run this daylighting simulation and analysis on each grid throughout the floor plate. And what that allows us to do is really look at the areas that are overlit versus underlit versus ideally lit, iterate through different shading strategies and facade design strategies, and predict how much of the floor plate is going to be ideally lit versus if it's under or overlit. And so this is a very powerful tool for studying different shading options, and taking an annual perspective, and then also at different times of the day and different times of the year, we can optimize those designs for those specific times of the year. Here's an example of a massing study. So these three floor plans here all have the same area, and we're studying the impact of the form and function of the building. So what we see here, and this is generally the case, is that the most compact mass will have the lowest energy consumption. If you hold all other parameters the same and just manipulate the aspect ratio of the building, you'll see that the most compact form will typically have the lowest energy consumption, because you're minimizing the amount of vertical wall area per floor area. So that's what we're seeing here, that center one having the lowest EUI. And just to mention, this metric that you see down here is called the EUI. This is the annual energy consumption of the building divided by its square footage. So that's kBTUs of energy divided by square footage. And that's what we call the EUI, or the energy use intensity, or energy use index. And so it allows us to compare different designs that may have different areas, but have similar sort of energy profiles. And here's an example of a parametric study, a sensitivity study, and we'll have more examples of this coming up. But basically what this analysis is doing is using, in this case, we're comparing two different massings, that's the red and blue line, and then we're comparing the impact of the U value, the window U value on the total energy consumption here. So we're iterating through 0.7 through 0.2, and we're looking for this point of diminishing returns, is what I'm showing here is circled. This is the point where improving the U value beyond this provides only minimal gains or returns on investment, for example. So we wanted to try to optimize how much money is being spent on the facade versus how much benefit you're getting back in return in energy savings. So, and again, you're seeing that, the comparisons on the mass 1 versus mass 2. Mass 1 is a more compact massing, and so for every data point, it's always a lower energy consumption. Now here's an example of how we can use how we would calibrate a model to existing conditions. So in this case, we were studying a project in Washington, D.C. that was an existing building that was pursuing net zero energy. And so the most important part of this is to get a high level of confidence in our energy model, so that when we apply energy conservation measures to the building, we have a high level of confidence that the resulting energy savings will be realized in real world. So what we're doing, you can see on these graphs on the left, is comparing the build energy usage, the actual utility bills, to what our model is predicting. And you'll notice it's not perfect, but when you get a statistical agreement between your predicted and your actual consumption, that's when you know you have a calibrated model. So we start out by calibrating a model to the existing conditions, and then we start to apply energy conservation measures like upgrading the glazing, using heat pump technology, heat recovery, those kinds of things. So it's a critical item for an existing building that's looking to get to net zero. And speaking of, this is an example of what we call the pathway to net zero analysis, where we could start with, on the left-hand side would be sort of the existing conditions, and then the examples of applying these energy conservation measures. And we're sort of stepping down, we call a waterfall chart. We're combining these energy conservation measures until we reach the point where our rooftop solar system can offset 100% of the energy consumption of the building. So essentially, we're looking for the most cost-effective set of options that are going to get our energy consumption low enough that we can support it with the roof. And that's what we're seeing here. And just to note here, this last step is very interesting for that project I mentioned in the last slide, is the AGU, the American Geophysical Union office building, their headquarters in DC, and they're actually using municipal heat exchange. So we're actually what we call sewer mining. We're taking energy out of the municipal sewer and using that energy in our building. And you can see it had a pretty big impact on our total energy consumption for this project. Okay, switching gears, we're going to dive into a case study. This is the Intuit headquarters down in Mountain View, California. So some critical things to keep in mind here as I go through the analysis that kind of dictated the energy profile of this project. So, and the analysis process we went through. So just know that this building is long and skinny, and it's oriented with those long and the long exposures on the east and west side of the building, which are sort of difficult from a shading perspective. It's an open office floor plate, and the client wanted this, the owner wanted this floor to ceiling curtain wall look. They wanted that visually stunning look to the building from the exterior and interior. So the third item that was very important to the owner is the efficiency and human comfort were very important. And so in some aspects, that third goal is at odds with number 1 and 2 there. So we'll talk about how we kind of overcame that in the analysis process that we went through here. So we started this project with a conceptual design charrette. So that's when all the stakeholders of the project are in the same room, from the architect to the owner, the facilities, staff, all the engineers, me, of course, as the energy analyst, and we're coming up with we're brainstorming ideas that would essentially lead to lower energy consumption, but also provide that human comfort component the owner was very adamant about. So part of this charrette was really focused on the facade and what we could do with the facade to make it perform for us. And so we studied 9 different options in detail, and I'm just going to review those quickly and show you the results. So the first 3 I call our curtain wall options, which sort of on the left is our base option of 85% basically floor to ceiling glass that's unshaded or untreated, sort of our baseline case. Then we looked at adding vertical fins, because remember we're on the east and west side, so vertical fins are what we need to use to be effective at controlling solar on those exposures. And then we looked at integrating a perforated shade. So you can see there we have a light shelf and then a perforated shade below the occupied level and a clear story unshaded glass above. These next 3 options are in here as sort of a baseline metric because we know that lowering the window to wall ratio will generally have a favorable impact on energy consumption. So we have these punched openings with approximately 45% window to wall ratio for these options, and these were studied mainly for benchmarking purposes to see how much of the impact, how much of a negative impact going with the full curtain wall floor to ceiling glass would be. So we've just got 45% punched windows with offset 8-inch deep. Then we looked at if you increase that offset by another foot or 18 inches, what does that do to energy consumption? And then integrating a light shelf into that punched window approach. And then finally, the sawtooth options, which were really the meat of the creativity that came out of that charrette. And so the idea here with the sawtooth, the one in the center, was the main design that we came up with, which was the idea of basically making the west-facing portion of the facade as opaque as possible, but then using the sawtooth shape to keep the north-facing portion of the facade with vision glazing. So you're able to take advantage of the sky, seeing the sky essentially to the north without the direct solar gain, which we're assuming will cut down on the cooling load because of reducing that direct solar gain into the space, but maintaining the daylighting benefits of getting that northern exposure to the west there. And so the other 2 options on the screen here are just sort of iterations of that. The one on the left is it's the same concept, but using a perforated shade instead of a fully opaque shade. And then on the right is integrating a light shelf with that concept as well. So my job was to analyze all of these conditions and come up with some recommendations. So here's the 9 options, just the view from the energy modeling geometry that we use to analyze this. And here are the results, the high level total energy consumption results. So between all of our options, you can see the EUI spread is from approximately 33.5 up to about 35. And so what is sort of surprising and was surprising to the whole team was that the spread between these options was not very large. So we're seeing about 2.5, maybe 3% difference between these options. And what was, several more, surprising things came out of this is that between just the unshaded 85% curtain wall and the punched window openings, we only see about a 1% difference between these. So that was pretty startling. Some of the other things that jump out at you here are that the options that we were using, incorporating shading, many of those options actually increased the energy consumption. And so that was sort of counterintuitive to the team. And so in order to understand why, we can look at the breakdown of the heating, cooling, and lighting energy, which are the main factors at play with the facade performance here. And so what you see, for example, if you look at the first 2 examples between the unshaded curtain wall and the vertical thin shaded curtain wall, what you see is very minor differences in the energy consumption and the heating and cooling between these options, but a pretty significant difference in lighting. And so by reducing the amount of light coming through the window with the fins, you're actually increasing the amount of electric lighting that needs to happen to keep the space at lighting set point. And so this is generally the case of what we're seeing with these shading options, is that the lighting energy is increasing more so than we're saving in either heating or cooling. And then when we look at these, the sawtooth options, which we thought were going to solve all of the world's architectural problems in this climate in particular, what we see here, especially this sawtooth facade with the opaque west module here, you can see the heating energy went up significantly, but only a minor drop in the cooling energy. And so what this is telling us is that Western passive solar gain is actually beneficial to this project because of us being in a heating dominated climate, even though you may think of California as a warm and sunny place. In the Bay Area, we actually still are largely dominated by heating in our climate. So what you see here is that the negative impact from reducing the beneficial passive solar gain is more beneficial than the negative side of the increased cooling. And so this highlights the main point of my presentation is that everything is about trade-offs with the facade. When you take an action, a passive action like using fixed shading to reduce the solar gain and help to improve comfort, you're also preventing that beneficial wintertime heat gain that can actually help the project. So everything's about trade-offs. And so for my clients were a bit skeptical with me based on these results because we all have this understanding that reducing the window to wall ratio and controlling solar gain should result in the most energy efficient building. So what we did is study the same approach, the same three sort of curtain wall, punch windows, and the sawtooth approach in different climate zones to see if the same thing would hold true. So down the bottom right is the Mountain View, our very mild climate, and what you notice right off the get-go is that every option is significantly lower EUI than the other climates, and that's really just because of how mild and nice our climate here is in the Bay Area. And so again, in Mountain View, we see the sawtooth option is a penalty. We actually increase energy consumption by using this approach. But if we look at a more extreme climates like Phoenix, for example, where it's much hotter, it's a cooling dominated climate, not a heating dominated climate, we actually do see a small benefit to this sawtooth approach there. And so this is when I breathed a sigh of relief to say, okay, well, this approach actually does work. It's just not, Mountain View is just not the right climate for this type of strategy. And then again, looking at more colder climates like Milwaukee and Washington, D.C., the same pattern emerges as does in Mountain View, where we're seeing actually a penalty from the sawtooth design, where that solar gain in the in the heating season is actually beneficial. So this is just just demonstrating how the trade-offs work and how that will vary by climate zone. Again, this is breaking out the same results, just breaking out heating and cooling. So looking at the Milwaukee data, you can see again that the heating energy went up significantly here with the sawtooth design, whereas in Phoenix, we see the cooling load drop, relatively small amount, and then the heating doesn't really move too much because of the climate there. So again, validating that approach, but not so much for our climate zone. So we're back to the drawing board. How do we make a decision given all of these results? We don't see a widespread in the results, and we're not seeing a clear winner on these innovative designs that we came up with. So what we do is typically make a pros and cons column and try to evaluate prioritize these different factors and see if we can come up with a selection here. So the curtain wall was the aesthetically desired approach from the client from our client, the architect, and the owner. And it provides deep daylight penetration. So more people in the office building will be able to access daylight with this design. The cons being there's a potential for discomfort for people sitting right up against the facade. And we saw that fixed shading is not effective at reducing energy consumption, and it would be very expensive. So those options, shading the curtain wall didn't seem like a great option with those fixed shades. The punched windows were the lowest energy consumption, but it was not the aesthetic that the owner was looking for. And so that also wasn't really an option for us to consider. And then the sawtooth design, it did prevent the direct solar gain, but it didn't perform as expected. And you can imagine that building those modules and that sawtooth design would actually cost a lot of money. So still we don't have a clear direction based on our pros and cons. And so this was leading us to was what we really need is an active solution, is something that's going to modulate throughout the day and throughout the year to balance those factors of solar gain, passive heating that we want, solar gain in cooling season that we don't want, and then the daylighting, the harvesting of daylight factor as well. So what we ended up with on this project is an automated shading system, and that's what I'm showing here. We actually have it is fully automated, meaning the building control system decides where those shades should be, and it's actually set up to optimize it for people sitting right up against the facade. And it actually allowed Intuit to increase the density of their floor plate by about 10 or 15% by getting people right up against the facade. So what this system will do is it's measuring the real-time sky conditions, so it knows if it's cloudy or overcast or how much glare is occurring in the sky essentially. And then it also knows the sun position based on solar geometry, and it can predict how that direct beam of solar energy will come into the building through the window. And so what these shades are doing is lowering the shades down just to the point where it prevents that direct solar gain on the occupants. And then as soon as that condition is alleviated, or there's no more concern for direct solar gain on occupants, it's raising the shades up. And so this corner condition is very telling here. So on the right side is the south side of the building, and so it's the middle of the day, it's about noon, so you see the south side of the shades are dropped. But on the west side, over to the left side of the screen here, the sun is not wrapped around the building yet, and so those shades are open further to allow as much daylight in as possible. And so what this did for Intuit is, first off, it does realize an energy savings, and we see if you compare automated shades versus manual shades, the idea being with manual shades, most likely, and what the research shows is that occupants will come lower their shades, to alleviate the glare condition or that direct solar gain, and they will leave them down longer than they should be. And so what that typically does is negatively impact lighting energy. So you don't have as much daylighting to harvest, and so your annual lighting consumption will go up. So this, you can see here in the utility cost summary, the automated shades does save, in this case, we were predicting about $1,500 a year, which doesn't sound like a lot, and it is not a lot. But the most important factor for this and for Intuit was that they were able to densify their floor plate and get 10 or 15% more people onto the floor plate. And so that was the big economic case for this system and why we ended up with it. So, and that's just a point to say, a lot of these energy conservation measures we study in this realm aren't, the adoption of them aren't necessarily driven 100% by energy consumption. There's other factors such as densifying the floor plate that come into play as well. So conclusion on this case study is that there are no universal rules of thumb for facades that apply to all climate zones. So depending on what climate zone you're at, you're going to have a different facade treatment, and that will, the energy savings associated with that will change based on climate zone. Now, I think I mentioned this earlier, but facade optimization is all about balancing those trade-offs and looking for the optimizations and balancing those trade-offs. Sorry about that. And so what we saw on this one is an active solution was required. And so in where these seasonal changes, especially in mild climates, an active solution may be required to truly optimize these items. Okay, switching gears into just more examples of parametric analyses that we've done throughout the years and the sort of lessons learned from those. So again, revisiting the window to wall ratio thing, what this graph is really interesting because it's comparing all the climate zones throughout the throughout the world, and it's studying the impact of window to wall ratio on the total energy consumption. So we see on the bottom, on the x-axis is going from 25% window to wall ratio up to about 90%, and we're studying all the different climate zones here. And so what this graph can tell you, there's several things that jump out here. So number one, this bottom line down here is the San Francisco climate zone 3C. And so what you can see is that it's dramatically below all the other climate zones. And so that's telling you that it's very mild here. And so the impact of the facade is going to be less impactful than it will be in other climate zones that are more extreme. The other thing you can see here is that some of these lines have a steeper slope than others. And so the steeper the slope of that line basically indicates how sensitive the facade is by climate zone. So for example, the steepest line we see on here is climate zone 8, which is representing the Yukon. So way up north in a very cold climate. So it makes perfect sense that as you add more glazing, the impact to energy consumption is going to be much more impactful than it will be in a mild climate like San Francisco. And so you'll see some of the lines cross each other. The slopes are flatter in some areas. So for example, in China, this Gansu, China, it's a very flat slope compared to, say, this New York line. And so what that is telling us is that there's other factors at play other than just temperature or necessarily outside air temperature. So it could be things like humidity, where if it's very humid outside, like it is in this climate zone 2A, it's going to be less sensitive to the facade because you're dealing with moisture content in the air as well. So just some very interesting kind of high level results from all the climate zones here. Here's some more, investigation into window to wall ratio with just a few different climate zones. But basically what we took here is an office building with 40% window to wall ratio, and then the same building with 70% window to wall ratio, and we compared it again in different climates. And so what you see is that the more mild the climate is, the smaller the delta between these, the 40 and 70%. So in somewhere like Vancouver, where it's fairly extreme and cold, you see a pretty large delta. Whereas within San Francisco, like we talked about in LA, it's more mild. You see a smaller delta between the two. So just driving that point home. Whereas in contrast to energy consumption, loading, peak load is a different story though. And so this is another sort of parameter that's important to consider, because sizing of equipment means real architectural space. So again, let's look at the example between San Francisco and Vancouver. You see a larger delta in the sizing of the cooling equipment than you do in the energy consumption of those two climate zones. And again, if we think about the next slide is going to show heating capacity as well. So if you just hold that San Francisco bar in your mind and see the delta between the 40 and 70% window wall ratio for cooling, and then we switch over to heating, you see the larger delta occurring in the heating load, and that's due to being a heating dominated climate. And again, so the smaller the equipment is, the lower the load is in the building, the equipment is smaller, the ductwork is smaller, and so it correlates directly to architectural space that you need for those MEP systems. So the point being, while energy consumption may not be the determining factor in a facade treatment option, the peak load that we're seeing in the building may very well be. Okay, here's some more parametric analyses, and I want to highlight the impact of infiltration here. So the highlighted options you can see at the beginning here are looking at heavy infiltration, medium, and light infiltration. And so I'll show, in comparison to all these other energy conservation measures that we studied, these items that are circled are the delta between our infiltration rate. So whereas changing the solar heat gain coefficient or the U value or the insulation levels in the wall seem to have relatively minor impacts on the energy consumption, we see a very large delta between these options that are varying the infiltration rate. So that goes to, the point here is to say how you build the facade is likely much more important than the actual components of the facade in many cases, in this climate zone in particular. And so what we advocate for wherever possible is building enclosure commissioning and really making sure the envelope is tight and reducing the air exchange between outside and inside. And so there's a couple ways that you can go about doing that, and that you see some examples of that here. So the one on the top is using our infrared FLIR camera. And so we can actually take a picture of the facade at night. In this case, we were doing this at night in Portland when it was about 20 degrees outside, and we're looking at how heat escapes from the building. And so what you can see up up here in this picture is that the bright orange sections of that facade is a frieze board that was not properly thermally bridged from the rest of the building. The architect had detailed it to be thermally isolated, but it wasn't built with that detailing properly. And so what we're seeing is a lot of heat loss. So if that surface of that frieze board is 53 degrees when it's 20 degrees outside, that means we're losing a lot of heat through that particular portion of the envelope. And so the contractor actually had to go and remedy that condition there. So the other thing we do, so the top one was thermal bridging impacts. The lower one is air infiltration change. So this is where we do blower door testing. We make the space negative pressure. So we make the entire building negative pressure so that air gets sucked in through the facade. And we're actually able to measure how much air is coming through the facade and compare that to the benchmark. And if it's not meeting target, then in many cases, the contractor will have to go and reseal the envelope at different places. So this is becoming more common as it's becoming code required in California and Washington and New York and several other places around the country. And so this is something we're advocating for and just preparing our clients to get ready to be required to do this. So the picture on the bottom left is just an example of how you find these leaks. So when you have the blower door in place and it's making the space negative pressure, you can use something like a smoke pen, and you can walk around and look for air leaks using the smoke pen. So in this case, we found a leak behind one of the face plates for the wall switch, and you can see the smoke is sort of billowing in from that point, so that we can identify that as a leak behind there and hopefully go and fix that. Okay, some more parametric sensitivity analyses that we're doing. So the next few slides are all going to relate to these three massings that we have here. So what you can see is approximately the same floor area between them. They're very slightly different, but a very distinct difference in the massing or the shape of the building, the aspect ratio. And so what you'll see is mass 1 is going to be the most compact form, meaning it has the smallest amount of wall area per floor area. Number 2 is long and skinny, so it's going to have a lot of perimeter versus core. And then obviously mass 3 has, by having that courtyard, you've effectively doubled the amount of wall area compared to the other options. So you'll see as we go through the sensitivity studies here how that flushes out. So here's a roof insulation impact study where you see the three masses compared, where mass 3 is always higher energy consumption than the other two, mass 1 being the lowest. And what you see here is that a little bit of insulation goes a long way. So an uninsulated concrete roof versus just adding R5 provides this big step down in energy consumption, and then adding another inch and 2 inches, 3 inches, and so on provides somewhat marginal benefits. And so in this case, we are saying 3 inches of additional of insulation would be all you would really need. Same concept with window U value here. So pretty decent benefit in energy consumption going from 0.7 to 0.6 to 0.5 to 0.4, and then it levels off from there. And the not too much benefit by going to 0.3, and then 0.2 is almost no benefit. So you might be wondering, why aren't we proposing a 0.3 U value on this particular project where we circle 0.4 instead? And this really comes down to cost and aesthetic. So we know that going to a 0.3 U value on a traditional curtain wall, that's really looking at triple film or triple pane glazing to get to those levels of performance, or non-metal framing. And so that's often not desired, and we don't see a huge return on investment by going with a higher performance in that. So window to wall ratio, we've talked about this a lot, but again, just looking at the different massings and selecting a window to wall ratio. In this case, it's mostly linear, so for every little bit of window we reduce, we get a pretty good benefit. But again, it's the aesthetic trade-offs that are important here as well. We don't want to be sitting in a dark box, because we want the building to look beautiful, and we want people to have access to views and connection to the outdoor. So solar heat gain coefficient, we see again a pretty good benefit by lowering the solar heat gain coefficient. Again, it's an aesthetic trade-off though. If we go down to 0.1 or even 0.2 solar heat gain coefficient, the glass is typically going to be darker and may have an aesthetic that the architect isn't interested in. So, shading projection factor. So in this case, we are looking at how deep the overhang can be or should be over the south-facing windows. So in this case, again, we don't see a huge benefit. We see a pretty good jump by adding a small overhang, but then going from there, a fairly minor benefit from adding deeper and more costly overhangs. Okay, and then just to summarize this parametric analysis, this is a chart that I really love because it conveys a lot of information in one view here. And so these are box and whiskers charts. And what that means is that it's showing all of the iterations of our models. We're summarizing them with the average being the mark in the middle of the box. And then the extremes are the whiskers. So it basically is conveying what's the average and then what are the extremes of these studies that we've done. So for example, this roof reflectivity box and whiskers are very tight and compact, meaning changing from the worst to the best performance of roof reflectivity had very little impact on the total. In comparison to the roof insulation, just to the left of that, you see, if you remember back to that sensitivity slide, the worst case performer was no insulation, and it was way up here, this whisker, but most of the other options with just a little bit of insulation tightened up the range of results that we saw there. So, and you get a sense from this type of a graph of how sensitive a given project is to any one parameter. And so by looking at this this chart here, we would say, well, the window to wall ratio is pretty impactful, and the external massing, the way you mass the building, is also extremely important. Whereas things like the south shading projection factor are not super important, and the roof reflectivity is not super important. Okay, so the key takeaways here. I'm not going to read all this, but the bullet points here are the important ones. So envelope commissioning, making sure the envelope is actually meeting the targets for tightness and leakage, are very important. Window to wall ratio. You want to prioritize window to wall ratio by view. So when there's nothing to look at, and I'll talk about this in the next case study as well, then it doesn't make sense to put floor to ceiling glass in an area where you have nothing to look at. But if there are views and connection to outdoor, you want to leverage that and increase the window to wall ratio where possible. Compactness in form is typically the most energy efficient, and I've talked about that in several examples. With the caveat that I wanted to make sure everyone realizes that unless you're doing a naturally ventilated project, in that case, when you want long and skinny so that you can get as much of the floor plate naturally ventilated as possible, and that can actually lead to the lowest energy consumption. Okay, and then into this, the final section of this presentation is a cold climate fenestration optimization. So this is the project in South Lake Tahoe. It is an office and admin building. We are using radiant heating, but no mechanical cooling on this project. So that is important in the way that we think about how the facade relates to total energy consumption as well. And we were using passive house design philosophy here because it's a very cold climate, and so we super insulated building and very low infiltration rates are what we were targeting with this project. So here are the things that we study that I want to review today. So as I called this, is a fenestration optimization. So really what we were looking at is placing glazing and the quantities of glazing that we should use to optimize the project. So option one, the architect wanted to increase the amount of glazing on the southern area, on the south-facing part of the building, because there was a beautiful valley to look at, and for people to have that connection to the outside. Where on the north side of the building was the parking lot for the building. So what we investigated was what would be the impact of just increasing the southern area of the building just by itself. And then number two would be, well, if we can sort of trade that off by decreasing the northern window area because it's a parking lot and it's not a beautiful scene to look at, can we trade off the perceived penalty from increasing the southern area by decreasing the northern area? Number three, we looked at the impact of the skylights, and this was really a budgetary thing. The architect had designed the skylights into the project, and the contractor was telling the team that these skylights are very expensive and would be, on the chopping block for the VE exercise. So the architect asked us to basically help them justify keeping those skylights. And then number four was looking at this, the big lobby area where we have curtain wall there for the aesthetics and connection to the outdoors. So what would happen if we use triple pane glazing in those areas to sort of compensate for the large amount of glazing we have there? So I'll step through each of those iterations and kind of show the results and how they relate to the project. So that first one was increasing the southern glazing area for the view purposes. And we saw the total energy consumption increase by almost 2%, driven by heating being increased. So we've increased essentially the amount of, we've weakened the envelope by increasing the glass area, and that is the lowest insulation point of the glass. So we saw the heating energy go up. We did see a small decrease in lighting energy because you're getting more daylight into the space, but it wasn't enough to offset the penalty in heating. So this option two was really looking at how can we compensate for that increasing the southern area. So let's decrease the northern area and try to keep the total square footage of glass approximately the same. What does that do to energy consumption? Actually, what we see is that it saved a total of 1%. So we've kept the total glazing area the same as in our original configuration, and but still delivered that increased glazing area on the south and realized a 1% energy savings. So this was a very positive finding and a great measure to employ for this project. Okay, the skylights one is pretty surprising actually, but when we think about the climate of Lake Tahoe, for those of you that aren't familiar with it, it makes a lot of sense because it is very cold, but it's also very sunny. And so what we saw when you remove the skylights, actually the lighting energy increased by 1% by removing the skylight, and the heating energy also increased. And that's because of the passive solar gain that we were getting through those skylights. And so almost a 4% energy consumption increase by taking away those skylights. That was a surprise to all of us and the team that it was that impactful. But again, thinking about it, the specifics of the project and the climate, it does make sense because it's a one-story building. And so, what's happening at the roof plane is going to be more impactful for this building because it's only one story versus, a 5 or 6 story office building. It makes a lot of sense that the skylights will be more impactful. And then just the nature of the climate, like I was saying, is cold but sunny, and so we get a lot of opportunity for passive solar gain. Okay, and then looking at that eastern lobby and improving, what can we do to improve the energy profile of that space? And so this came about from us looking at our modeling results, and why I'm showing this graph here is what this is model output. What we're showing here is the heating load or the heat flux through the space due to the envelope for every space in the model. So that's why you're seeing a bunch of different colors. The black line is this eastern lobby. And so what you can see, or what jumped out at us, is that the loads in this lobby are many times larger than any other loads in the building. And so that tells us for a project that's pursuing passive house standards and net zero energy consumption, we really should not be seeing, one space in the building driving energy consumption or really driving the peak load in the space. It's just not the design philosophy we should be aiming for here. So we wanted to look at ways to remediate that, and so we looked at adding triple pane glazing. And I will say that very rarely in my experience has triple pane glazing been a benefit to the point where it would pay for itself. But in these very cold climates and on smaller buildings like this, it is absolutely impactful. And in this case, it paid for itself very quickly. So by going with a triple pane glazing where your U value is below 0.2, we saw a big decrease in heating energy. So 8% reduction in heating energy, which may not sound like a lot, but it is a ton when you compound it over the life of this building. On building total, we saw a 5% reduction in energy consumption. Again, that is very large for one energy conservation measure and limited to just one part of the building as well. So again, a very impactful measure that we proposed to the client. And when we look at the grand total, the way the sort of the project unfolded, where we started the project based on the architectural design with an EUI of 45.1, we're increasing, adding all these energy conservation measures together, and we're lowering the EUI down to 42.5. So that is about a 5 or 6% reduction in total by combining these measures, which is, like I was saying, may not seem like a lot, but 5% compounded over the life of this building year after year is actually a lot of energy, and we don't very often see this impactful of measures just related to the facade. So again, highlighting what I was harping on before is that it's very much climate dependent, the way you treat the facade. And where in a mild climate, seemingly big changes to the facade results in very small differences in energy consumption. In a more extreme climate, seemingly very small adjustments to the facade can have very big benefits to energy consumption. So that is the main takeaway I would like you to take from this presentation. And that is all we have here for you today. So I'd be happy to answer some questions, and I hope you all found this enlightening and useful in your work. So let me have a look at the questions. Someone asked, where's the attendee sign-in sheet? So if you can just give us your AIA number, and even in the chat box here, we can make sure to give you credit and follow up with you for that. Let's see, I'm having trouble seeing all the questions here. No, we got some more. There we go. What is the climate zone for the Intuit project? So that is climate zone 3C from ASHRAE climate zone. So that's in the Bay Area. In the California climate zone, it's climate zone 4, if you're curious about that. Let's see. Yes, the climate, yes. Leroy was saying the climate zone, the climate appears to be very mild. This could explain the narrow delta for each option. Yes, that's the point I was trying to make. So, okay, a question from Sydney Kim. So when you are exploring facade optimization, isn't peak load more adequate metric than EUI? That's a very good question. I would say it depends, right? So the more extreme climate, it may be. In a more mild climate, it may not be. So the loading, the peak loading, certainly the delta is wider between the two. However, how that relates directly to architectural space and cost, it may not be over the life cycle of the building, may not necessarily be the most important factor. So it's a good question, but the answer is, I guess it depends on the specifics of the project. Let's see. Leroy says, the code also needs to be mentioned that continuous installation requirement is what the architects follow when detailing the frieze. Yes, that's true. So in that case, there wasn't a code requirement for continuous installation for that project in Portland, but the architect had actually detailed out a way to thermally bridge that, and the contractor just didn't build it that way, unfortunately. Let's see, from Paul. Well, that's his information. See, Juan says, did you also analyze the impact in terms of glare reduction at the moment of applying shading strategies? So we did not on that project. Interface did not. There was another consultant looking at the impacts of glare and doing the daylighting study on that project. However, that is what we would typically do on a project, is we would look at the energy consumption in conjunction with the daylighting analysis to say, what's the more important factor here, and try to co-optimize those things. So obviously in a mild climate where we're not seeing a big delta by energy consumption due to facade options, we would defer to the lighting analysis, to the day lighting analysis, to dictate which of what's going to provide the most occupant comfort from a glare perspective and daylight availability perspective. So I hope that answers your question. Of course, you want to co-optimize those whenever possible. Let's see. Barry says, in DC, we are now being required to calculate thermal bridging. How significant is the delta between thermally broken balconies, parapets, and connections should we anticipate? That's a great question. I don't have any material prepared for that, but we've been being asked the same question. It's a bit difficult to study with a typical energy model, from the annual perspective, because it doesn't typically factor in the physics of that connection or the fin of the balcony overhanging. So what you would have to use is a tool like Therm, which I showed at the very beginning, to analyze how much heat is actually being able to transfer through that balcony connection. And I have more recently, I was seeing someone on LinkedIn promoting a new product, a structural engineer it's basically a it's an insulating material that also has a structural component that allows balconies to be thermally broken from the rest of the construction. So I will make a point to get some information for that for the next round of this facade study. And then Leroy asked, have you included mass timber as an ECM? Again, I don't have anything prepared specifically for that, but the mass timber benefit, I did see this on another project in the Bay Area recently where, they're using mass timber and it needs to be so thick for the structural reasons that it ends up providing a substantial amount of insulation to the project. So whereas say a typical, in this case, they ended up with like an R45 roof just by having the mass timber included as part of the roof structure. So really what the mass timber motivation there comes down to embodied carbon in my mind, and aesthetics and being a renewable resource to build with, less so specifically about being insulative. But still a great question. Okay, thank you all for your questions. That's all we've got for today. I hope this was an informative session for you, and we hope to, be able to give back to y'all and help you all with your projects in the future using these types of analyses. So again, thank you very much for coming, and I think we have another webinar in 2 weeks, so I hope to see some of you again, and have a great rest of your day.
Steve, thank you very much. That was a fantastic presentation. And yes, please do keep an eye out. We will be sending invites out next week for our next session, exactly 2 weeks from today. So thank you.
Thank you, everyone.